Hello everyone. Today we'll be looking at the solutions for the Leetcode Weekly Contest 397. We'll be discussing all 4 problems and their solutions. Alright, so let us discuss the problems. Start with problem 1, permutation difference between 2 strings. So it's a pretty simple and easy problem. There's an easy tag also to this, and if you read this, you'll get this problem in one go. Alright, so you will be given 2 strings S and T. So 2 strings are given to you, and every character occurs at most once in S and T. So if there is some character that occurs in S or T rather, it is only going to occur once. And then it's also given that T is a permutation of S. Now what do you mean by permutation? That means T is made after rearranging the letters in S. Alright, so T is indirectly it is exactly S if you sort S and T together, but T is just a rearrangement of S. So now it's given that the permutation difference between S and T is defined as the sum of the absolute difference between index of occurrence of each character in S and index of occurrence of each character in T. So now this sentence might look pretty easy to it might not be very easy to understand, but then it's a very basic concept they're asking you to find. Let us try to look at this like this. Let's say you have the string, let's say I have the string S, and let's say that string was A, B, C, D. And then the new string T, I rearrange the new string tree from S. Now I know that in S, remember, I'm always taking only one occurrence of a letter. So if I have a D, let's say, or a B, let's say, there are not 2 Ds, there is only 1 D, right? Similarly, there is no 2 letter coming. So it's all one that's coming in the string S. And now if I make T, let's say maybe T is some rearrangement of this. Let's say maybe B, C, A, D, something like this. This is also a rearrangement, right? So now what they're asking you to print is, like, you can store the occurrence of, let's say, if I ask you what's the occurrence of the letter A in the string S. So if I have a 0 based indexing, this is 0, 1, 2, 3. So you will say in S it's 0. And if I ask you the same question for the string T, you will answer that in string T, the letter A occurs at the second position. Yes? So now if I ask you what is the absolute difference between these two, you are going to say absolute difference is 2. Now this thing is done, the phenomena I showed you, I have to do this for every letter that exists in S. So I'll do this same operation for B. I'll calculate the B's index, that's 1. And then I'll be calculating the index of B occurrence in T also, that's maybe 0. I find the absolute difference, and the absolute difference turns out as 1. And then I do the same for the letter D, I do the same for the letter C, and the letter D. And when I add everything up, whatever the absolute differences come out to be, that is going to be my answer, right? So pretty simple question to understand. If you can check out this theory I just told you on the test cases also, you will say, yeah, that's working definitely. Let's say for A, B, C, B, A, C, they have given you a very nice explanation that if you take A in S, that's the 0 position, A in T, that's the 1 position, so absolute difference 1, plus 2 minus 2 plus 1 minus 1, that's the answer 2. So how do I now implement this? Now there can be various methods to implement this, because I know that size of the string is very less. So I can maybe take an unordered map, a vector, whatever I want. Target being that I somehow am able to store, target is store the index of occurrence. And I have to do this for both S and T, right? All the letters in S and T, I have to store their index of occurrence. If that is done and dusted, then I can simply take a variable answer and just add on to that whatever comes out as the absolute difference between both occurrences for the same letter in S and T. So I can say absolute difference. Let's say that letter is CH. So I'll say whatever is the occurrence in the S letter, S string for, let's say, the character CH, minus occurrence in the T string for that same character CH. This is going to be my answer. Alright, so now implementation now is not going to be a big part, because if you have understood that what I'm trying to do, then that's going to be pretty simple, right? So I have implemented this with a very simple approach, taking a vector of 26 size with everything as 0. Now why 26? Because I am trying to represent every index as a lowercase English letter. How do I do that? This is for you to note. For all the beginners, you can actually take this something like this, that in a vector, if you want to create something like a frequency, there is something called as ASCII values in C++. So what you can do is, or not exactly in C++, in general programming languages. So in ASCII value, what it dictates is, let's say I have the letter A, it is mapped to a value, to be very specific, it's I think mapped to a value 97 in ASCII format, and from that on, B is mapped with 98 and so on. So this is just values that are denoted till the letter Z, and then what you can do is actually, you can say that I will extract S of I, and then I will subtract the ASCII value of the letter A from this, and this index can be, this value can be used as an index to, let's say this is the occurrence vector OC, so I can say OC value becomes equal to I. This is the crude statement I'll write to actually implement my thing out. So let's say the string was actually, maybe let's say string looks like D, E, F. So in this you would actually go to the first letter, let's say D, and the ASCII value of D minus the ASCII value of A will give you the index which could have been mapped to store D. So ASCII value of A is going to be 97, and then this is 98, 99, 100, so this is 100. 100 minus 97 gives you 3. So at the third index of this vector, of the 26 size vector, this is the last index 26, this is the first index 0. At the third place, 1, 2, 3, you will store whatever was the occurrence of the letter D, that would be I. In this case, I is 0, 1, 2, so this I is actually 0. Similarly is done for E and F. So this is just a small trick for you to have a revision on ASCII values. Again, you can implement this with map, even an unordered map, just any data structure which helps you get your work done, get you a good amount of occurrence of every letter in S and T. All right. So let us deep dive into the code part, and that's going to be the full thing to see. So I have created two vectors, A and B. Now A is the occurrences for the string S, and B is the occurrences in my analogy for the string T. Both have 26 size, starts with 0. Right, so I'll start in the string to iterate, and then writing this sentence as I told you. A of S of I minus the letter A is equal to I, and B of T of I minus letter A is equal to I. So every possible letter in S and T for the same ith and that day, because the size is same for both, right? S and T size are same because T is a permutation. So the ith letter in S and T, both with their ASCII values together considered as an index, gets saved or has a new value, that is I kept over there. So now I know that if that letter is kept with, if that position has some I value kept over there, that's actually the occurrence of that letter in the respective string. So then C becomes my answer. This is just a variable I took. I iterate from 0 to 26, less than 26 actually, in both the vectors A and B, and then I simply add the absolute difference of AI minus BI, and then I return C. So I'll dry run on one case. Let's say I'll talk about this case. All right. So let us dry run on this part. You have A, B, C, D, E, and then you have E, D, B, A, C. So what I'll do is I have vector A, this is vector A of 26 size, this is 0, 1, 2, 3, 4, and 5 index, and 6 index, so on. And then I have the same thing for, I should say, the occurrence storing for the vector B. So this is again so on till 26 size. All right. Now I have the occurrence, I have the indexes over here 0, 1, 2, 3, 4. So first I'll talk about the string S. How do I do the mapping? Mapping is done simply. A goes at 0, B goes at 1, 2, 3, and then I have a 4. And then what about this? I have E kept at the 0th. So E is 0. That means 0 over here. Then D is at 1. So this is 1. B is at 2. So this is 2. A is at 3. This is 3. And C is at 4. This is 4. Now, when you calculate the absolute differences, you will find this absolute difference is 3. This is 1. This is 2. This is 2. And this is 4. Right? So if you add everything up, I think you should get the correct answer, right? Add everything up, you have 4 plus 4 plus 4, that is definitely 12. Well, it's a basic approach, like I mean, it's not a very hard question, but might be like implementation might be stuck in somewhere. So that's what the solution is for. All right, so we will move on to the next problem, right? What we can do is actually quickly discuss the time complexity for this part, right? So as per my code, I will have a time complexity of O of, I should say n is a good size, right? And for space, because I'm storing some space to store the indexes, that's also in O of n order, correct? Or O of 26 order to be specific, because I've put a constant limit on A and B. Considering that I like knew that I have only the length in 26 and lowercase English letters. So O of n of 26 is good. And even like if you take O of n is actually like maximum 26, which is almost constant, because like 26 iterations is almost nothing, right? If you look at the larger picture. All right, so I'll submit this out and you can see it gets accepted. All right, so moving on to the next problem. Taking maximum energy from the mystic dungeon. All right, so in a mystic dungeon N, magicians are standing in a line. Each magician has an attribute that gives you some energy. Some magicians might give you negative energy. That means they're subtracting the energy from you. So basic stuff. N magicians standing in a line. They have some attribute. All right. Now you have been cursed in such a way that after absorbing energy from the ith magician, you will instantly be transported to the I plus kth magician. All right. This process is repeated until you reach the magician where I plus k does not exist. All right. So now I'll give you a brief about this question. Like imagine the numbers in the array, that's the magician attributes, are like A1, A2, A3, A4, A5, A6, so on. Let's say till AN. Now let's say if k is equal to 3, what they mean to say is you choose any place where do you want to start. So let's say I choose myself that I'll be starting off with magician number A3. But when I actually start with the magician A3, if I take its attribute, I actually take its attribute value, that is A3 in my current, whatever you can call that, power, energy, whatever, I will have to jump 3 indices and I'll be forced to jump to the next number being A6. So this is where I'll land. Then I'll be forced to jump 3 again, that this is where I'll land. So the initial place I choose of starting is definitely my own. So I know that I can start maybe with A3, maybe I can start with even A2, maybe I can start with even A1, maybe A5, that's totally up to me. But when I actually start from some position, I'll be forced to jump and take all the attributes at k intervals of given fixed, gap. Alright, so this is actually the problem. Now they're asking you that because of this curse, whatever phenomena, whatever this happens, whatever you try to simulate, tell me what is the maximum energy you can actually gain. So the question only boils down to how optimized and how greedily you are able to choose the best position which you think you should start, and from that position you will be forced to pick up k gap of intervals till it's possible, right? It's again written till it's possible. That means if I plus k does not exist, that means you will not jump anymore. All right, so till it's possible for you to do this, you will look into the picture and figure out the maximum energy. Alright, so now how do I approach this problem? Now again, brute force solution, if that comes to your mind, if I look, let's say I take a look at the test cases. So this is 10 power 5 test cases. Alright, I have a 10 power 5, sorry, not test cases, size of n rather, which is the energy. I can say energy size is actually n. Now you can be like, all right, let me do a brute force solution and let me maybe put up a for loop and go to every index. From that index, again, let me jump the boundaries, maybe let's say like from starting at some I position, then jumping again, then some I position jumping again, then some I position jumping again, and so on. And this might work. Now, like at first glance, it should work, but then I'll give you a test case for which the worst case time complexity will be very bad. Like let's say k is equal to 1. K can be definitely 1. This is something I also saw. So this is something you can also observe, that constraints might give you a very good approach and very good idea beforehand even starting your coding part. So if k is 1, let's say, and the energy length is 10 power 5. So let's say I have 10 power 5 to be the n value and k is 1. That is, you have to jump only one time. That is almost saying I am not even jumping, I am just taking consecutive sums. So if I have a I variable that runs from 0 to n minus 1, and then I have a j variable inside this, which is actually taking that, oh, this is my, I am jumping like this, so on. And then because like this becomes my, I becomes my starting position, and then j is trying to jump one time, or rather k is helping me jump one time. Then you can actually imagine this complexity to be an order of O of n square. Yes, because what will happen is, let's say the 10 power 5 array is given, you will be first standing over here, then you will jump one time. So this is going to have n iterations. Next time you will be over here, you're again going to jump one iterations. That's going to be n minus 1 iterations, and so on. So if you imagine the sum of iterations in this way, you will get an order of n square, right? N plus n minus 1 plus so on. So this is actually a sum of like this is like sum of natural numbers can be like initiated with this, or you can simply call this as sum of AP. You find the sum of AP, you will definitely find that the order is almost n square. So this is not going to work. I need a better solution than this. And like I just showed you a test case that for k equals to 1, it's giving me an n square solution. So might be for other cases, it might work faster. Let's say if k was a big value, maybe 4, 5, it has a bigger jump. But then for k being 1, you are going to have a problem. Alright, so once that is cleared up, we actually try to look at some quick observations in the array itself and in the logic itself we are trying to build. So let's say I have the array A1, A2, A3, A4, A5, A6, let's say till I have A6, alright, so I have 6 numbers. Now imagine like let's say k was given 2 to you. Then what would essentially happen? Like essentially what would happen is all the numbers, can you think that if I have given k equals to 2 and let's say I start at A1, then A1, A3, A5. All these 3 numbers, I'll write this A1, A3, A5, they belong to a same configuration set. As in meaning they have the dependency of 2 gaps. Yes. So let's say tomorrow if I start off with A3, I'll still remain in the same set. So the set of A1, A3, A5 actually occur together because they have the 2 gaps with them, with a beginning position at A1. Similarly, the next set is from A2, A4 and A6. I have a set that is A2, A4 and A6. Now let's say I'll do something more. Let's say k was given 3 to you. In the same question, I will have a set that's formed of A1 and A4, a set that's formed of A2 and A5, a set that's formed of A3 and A6, and that's all. So can I not picturize that I can break down my main vector into almost like mathematically how does it come out to be like let's say I have like if it's divisible, even if it's not divisible, like because I'm not taking approximate case, but approximately you can say that I'll be breaking the whole array down to n by k new different arrays. Can I do that? If I, let's say in this case only we saw that n was 6, so I broke this down to n by k, not n by k. If like in this case we saw that approximately I can break this down to k arrays. Yes, k different arrays. Is that right? And the k different vectors which I'll be breaking this whole thing down to, what I can do now is, like let's say I'll talk about this piece of code only, A1, A3, A5 and then A2, A4, A6. Individually, these are 2 vectors. And remember, what it is written in the question is, if you are standing, if you think that you start at some position, let's say I pick up this position to start with, from here I will always have to pick up all the attributes of the magicians at k jumps. So if I start at A3, automatically everything after A3 which falls in the set configuration of A3 has to be taken. Similarly, if I start at A1, everything after A1, including A1 obviously, in the configuration jumps of A1 has to be taken. So if let's say if I ask you, if you have these 2 vectors given with you, which are the only possible configurations of jump, can you not simply run some sort of a suffix sum approach in these 2 vectors individually to find your best possible sum? You can. Imagine like this. If you take up the first configuration, that is A1, A3, A5, what I can do is I can run my sum variable from the right hand side. I initially say that I will be adding the sum A5 and this is my best possible answer. I'll argue that this is my best possible answer. Maybe. Let's say I have some answer, I store in that thing. Then next time I will add on A3 to this and my new sum variable will look like A3 plus A5. Now this represents the sum of what if I could have started at A3. If I would have started at A3, I would have been forced to take A3 and then all the next numbers which fall in the A3, the bracket of jumping 2 from A3, that would be only A5 as clearly visible. So the sum currently is A3 plus A5. Now I can maximize this sum value again with this answer variable. Next time I jump back, I have A1 plus A3 plus A5 getting added to some different variable. Let's say that current variable that's maintaining is S. So I can maximize this S variable now, that's the new value A1 plus A3 plus A5 with this answer variable again. And once this is done for this array, it can be again done for this array, because now in this array I was able to cover all the starting positions of A1, A3, A5. Now I can cover all the starting positions of what if the possibility I had of starting with A6 or at A4 or at A2. But now what I did is, like what the problem in our initial approach, we saw For k equals to 1, we are getting an n square complexity. Let's try to analyze this. Now, if you have the array a1, a2, a3, a4, a5, a6, let's say, and so on till maybe the largest number, an, and n is actually in 10 power 5 order. What would happen is, k being 1, you will only create one vector. Yes? Why will you create only one vector? Because you're only jumping once, right? You're only jumping once. In this, I said that because you were jumping twice, so this was a jump, and then this was also a possible jump. But so you had two different sets of configurations starting at two different numbers, a1 and a2, right? Or that's clearly visible. But I know that in this case, if k is 1, I will only have one set of jumping, that is the array a1, a2, a3, a4, a5, a6, so on till an. And now in this array, I just need to run an iteration from the right hand side after I've computed this array. So this computation is something that's outside the for loop. Now I have a new for loop that helps me go inside this vector, run a suffix sum type of an approach, and find the best possible suffix sum. So that this is obviously suffix sum, right? What I'm actually calculating is actually suffix sum. So best possible suffix sum in this array, or simply saying that from the back, which position should I start with, for which I will have to take that number and all the numbers coming on the right side. So, and that can be maximized with my answer variable. So what complexity do I have of this creation of this jump sort of a vector with k1? I will have a maximum O of n complexity, because there is only one vector. So every time I push back in some vector, some data structure I want to maintain, that is all that is going to happen. But then to run this suffix sum approach, that's also in O of n. And that's pretty clear, right? I have O of n only because I'm running a simple suffix approach. So can you see that I have optimized my complexity a bit? All right, we have definitely optimized my complexity a bit. So what I'll do is, how to implement this out, I will create some vector, I will create a vector of, you can say vector, all right, and what I'll do is, I'll vector of vector as in like 2D vector of int type, and then I can actually, the size of this initial vector, I will maybe maintain the size as maybe I took directly this as n, alright, but then again, I think it's pretty obvious that approximately, when I said approximately k, I think maybe not approximately k, you can actually argue that I would have exactly a possibility of creating exactly k total configuration sets, maybe you can call them, for the jumps, right? So if k is 1, I had 1, if k is 2, I had 2, if k is 3, I will have 3, if right, so yeah, so that can be definitely taken up into the picture, right? So considering that to be the case, what I can do is I can create this vector size to be even, I can create this vector size to be n, right? Because I know n is not going to be a problem, and k is also less than n, so whatever I create, that's not a problem. What I'll try to simply do is, why am I making a vector? Because every row of this vector that is related to some index, so this is your index 1, 2, 3, 4, 5, over here where there needs to be stored a vector, there needs to be stored a vector, and so on. I am going to utilize the index value to actually tell me which configuration set am I talking about. So that is going to be represented on the first value I take. So let's say I'm talking about the configuration set, this one, a1, a3, a5. So this vector gets pushed at the 0th index. Then this vector gets pushed at the first index, and so on. This is how I will tackle the problem. So how do I do everything how do I implement this out? All right, so I'll push back in the vector, and once that is done, all that would be left for me to actually go in the vector of vector, and then for each vector kept at each ith index, I'll be calculating the best possible suffix sum. All right, best possible suffix sum. Now let us try to imagine the time complexity. I showed you for k equals to 1. I'll argue for more. Let's say I have a general k. If I have a general k, what would happen? What would happen if I have a general k? Let's say I'll take up something like this. If for a given n value, you actually come up with 2 configurations, then the size of that vector of vector would be 2. So a for loop, outer for loop will run in 2 iterations, and then the inner for loop for every array. Now because you had total 2 distribution or 2 configurations made out of the n array, you know very well that the size of every array would approximately be n by 2, because it's just halved. Yes, if I have 2 vectors, I have kind of grouped them into 2 different sets, and every set has maximum size n by 2. So being that the case, the inner for loop is going to run in a maximum iteration of n by 2. And then this has a very clear dependence, clear relation. Next time, if let's say I had divided this into 3 sets, if I divide this into 3 sets, then the size of every array will be n by 3 also. If I divide it into 4 sets, this is n by 4 if divided into 5 sets, and so on, so on. So overall, if you look at the complexity of these two for loops together, if this runs in, let's say, k iterations, then this runs in n by k iterations. And that is actually the k part I'm talking about. So can you not see that overall complexity is actually n by k into k, which is actually O of n. So approximate an order, right? An order is still maintained as O of n. And O of n order is very good to work with, because since I have a solution, I have an energy length in 10 power 5 order, it's very clear that O of n solution is going to definitely work. Alright, so this is how we can solve this problem. Now let us look at the code part and understand how can we implement this out. So I have taken the energy size, that's n. Now I'll create the vector of vector, initial size n plus 1, not a big deal. Like, you just need enough indices to actually store this out. Now I have taken a variable c, that's actually the indice. I can maybe better name this. This is the index. Alright, this is the index, and then what I'll do is I'll go in the array 0 to n, and then I'll push back in this current index. So if this is the index, I'll push back in this current index the energy of I, and I'll increment this index. And whenever I feel that this index has gone, like has become equal to k, I will reset this index back to 0. What does this mean? Like, how will it happen? So let us try to just dry run this out very clearly. Let's say I had these numbers, right? So I had A1, A2, A3, A4, A5, A6, all right? And let's say k was given 2 to me. So what I'll start off with, index starts off with 1. So in the I have definitely, like, I have enough space in the vector. So let's say this is index 0 vector, and then this is index 1 vector, and then this is index 2 vector, and so on. Like, I don't require a lot of vectors, but let's say assuming like this. Now I'll be at this number. I'll push back in the current index A1, and then this value turns to 1. Next time I go to A2, I push back A2 in the first index, that's index 1. So this is A2, comma. Now index becomes 2 and it's reset back to 0. So next time I have actually pop at A3, I'll be pushing back A3 again in the 0th vector's last position, that is A3. And then this pushes in A4, this pushes A5 over here, this pushes A6 over here. So what I'm trying to do is indirectly, because I know that A1, A3 and A5 numbers need to be pushed in the 0th vector with correspondence, like A2, A4, A6 need to be pushed in the first vector, and so on, whatever could have been in middle, considering k might have been bigger, n might have been bigger, you can just imagine, visualize that out. Target being, somehow I'll implement the code to actually push back the numbers which have the same, I want them to go in the same vector in the correct locations. So however you implement this out, it's totally up to you, alright, and that's not even a big deal of the whole code, but yeah, that's how I implemented this out, alright. So now once I've done this, I maintain an answer is int min initially, alright. So because why int min? Because answers can be negative also, right? Energy is negative also, and the maximum energy negative can go is negative 1000 into, maybe I take up everything, so that's 10 power 5. So I have taken a very like lower bound in this int min is good enough. I iterate in every vector, so I go to the it is the vector that is there. Now if there does exist some size of it, that means there are some numbers in that configuration. So if there are some number in the configuration, what I can do is, this is the suffix sum, so I can call this suff sum, and what I can do is, I will iterate from the back of the vector, that is it dot size minus 1, I is greater than equal to 0, I minus 1 is, and then I add this suff sum, it of I to this suffix sum, and then I will maximize, every time I calculate a suffix sum, I will maximize that value with the answer variable. Alright, so this is definitely going to work. If you see, I'll submit this out, gets accepted. If I talk about the time complexity now, alright, so as we discussed, like, it might look at a glance it's n square, but it's not n square, right? It's not anymore n square. So if you look about this complexity is definitely O of n, right? You're nothing doing, just taking the array and pushing back every elements and iterating. So this is O of n. But this mean for loop which I've done over here, this might look a bit different, but then try to understand this with pen and paper. You will easily figure out that this complexity is not actually going in the upper bounds. If it was actually going, we would have gotten a TLE, right? So it makes sense. So this thing is going to run in whatever number of breaking downs I have done in the vector v. So let's say I have as I said, let's say I have k configurations which I broke the whole vector down into k sets initially, then this for loop would run in the size of that k sets, and I know that the size of each k set is going to be in n by k size. Yeah, that's very clear, clearly visible even from this case also. So I know that the overall complexity of this for loop can be written in an order, like it can be reported as in an order of n O of n by k into k, which actually is like something written like O of n. And so I'm giving a very rough estimations, alright, but then again, target is to get the whole thing down below 1e8, 1e7 operations. So that is definitely what we are doing. So I can write O of n as a good time complexity for this. Now what about space? Now I am definitely using some space, right? I am using a vector of vector to store this out. And in the vector of vector, I know like if I want to optimize, like if I want to exactly put out the space, I will have definitely, I have created an n size of the rows. So I will definitely have n rows. Now into whatever is the maximum capacity that a vector can take when I take the score sum. So that's obviously like I'm starting off k jumps, so maximum I can actually create is n by k. That's individually each column's size. So this is a good, this is the complexity. Alright, so general I can say complexity of the space, which I can say it might go into, alright, so not n over here actually. Not n actually, this should be actually k, right? This should be actually k. So obviously because like I have the k is the maximum number of rows I would actually use up, you can say. Alright, so overall like even the space is I think in O of n order might be a good order to report. Like that's a good order to report, right? Because overall you can say that I am still working with the distributions only of the different sets. So that's the maximum size in the rows and columns also I would gather. Alright, so this is a good estimation I think for time and space, and yeah, definitely gets accepted. So that's done and dusted. Let us move on to the third problem now. So question 3, maximum difference score in a grid. Alright, so let us use this problem. You are given an n cross n matrix grid consisting of positive integers, and you can move from a cell in the matrix to any other cell that is either to the bottom or to the right, that is not necessarily adjacent. Now, the score of a move from a cell with a value C1 to a cell with a value C2 is C2 minus C1. Alright, so if you're moving to some cell, you will take that value first and then you will subtract the value which you were at the current cell C1 from it, and that's the score. So you can start at any cell and you have to make at least one move. Alright, so we need at least one move and return the maximum total score that you can achieve. Alright, so this is the given problem, and like let us look at the test cases. They have written like for this grid, what you can do is start from this 5 over here, right? 0, 1 cell, then move on to the 7. That's a difference of 2, and then move on from this 7 block to directly this 14 block. So that would be 7 to 14, that's 14 minus 7 backwards, that's 7. So 2 plus 7 is 9, and the argument is, according to them, this is the highest sum achievable. Alright. And similarly for this part also, highest sum achievable is -1. So you can have negative scores possible, but the target is the maximum score that can be achieved. Alright, so now if you look at the N and M section, you have 1,000 each order of N and M both. That means the grid is in a maximum 1,000 cross 1,000 order. So in a 1,000 cross 1,000 order, what does this mean? It gives me like it gives me the hint that I need maybe the order, like the best order I should actually do is n cross m. Like I should maybe create some solution that works in n cross n complexity, and that way I would be very good to go, right? So that is what I'll try to figure out in my solution. Now at one glance, you will maybe look this solution as a solution that might have some recursive or some sort of a DP solution maybe, right? Looking like maybe you're standing at some current cell and then maybe you try to jump to some other cell, and then you know that the maximum jumping you can do is either in the right part or in the bottom part. Let's say you're standing at some I, j cell, but then we actually have a better idea in this, like jumping from I cell in the same row to some place or same column to some place and then figuring some maximum score. I mean that's going to give you a very high order, because the problem is you can start at any cell. So just to implement this, you will have a n cross m complexity that already gets utilized in the 2 for loops to actually go to every cell. Yes, so this sort of a solution will not work. That's definite. I need some better thing than that. So Actually, the whole question was about a very small observation if you could create. And from that observation, this problem was actually solvable. Once you actually make this observation, the problem is going to be very easy. All right, so what was this observation? Let us discuss. So what I'll do is I'll take up some numbers. Let's say the number A, B, C, D, E, F, G, H, I. Let's say I have a 3x grid that looks like this. 3x3 grids that looks like this. Now, let's argue, let's argue that, let's say according to you, the solution, the best score came from starting with B, jumping to H, that's the so I cannot go to the left part or the up part, I just go to the bottom part, and then from H, I cannot go any bottom, so just the right part. Let's argue that the next best was I. So the argument was B to H to I was the best score. Now tell me, if I actually create this score, like if I ask you what this score is going to look like, this score is going to look like obviously H minus B plus I minus H. Is that right? That is what this this overall score is going to look like. Because like if I am standing at B, from B I would be trying to jump to H, and from H I'll be trying to jump to I, so that gives me this score. Now, if you actually sort these terms out, you get something that looks like I minus B. Now, what is this? What does this indicate? We followed a path from B to H to I, but all we ended up was the start and the final difference. Can we see that? If wherever we ended at I, can be called as the final cell, and wherever we started off, if you call that as a start cell, the actual difference of terms will only end up being final minus start, because everything in between has an alternating plus minus structure, so it gets cancelled out. This is the actual and the very most important observation in the problem. Now, with this observation, we can actually deduce a very quick thing, that I don't need to follow a path, because I know that if I follow some path and I try to take more than 2, 3, 4, 5, 6 cells, it doesn't matter. It only matters that what was my start and what was my end. So by this logic, what I can do, by this argument, for every cell that is out there, I can, in my ideology, what I did was, let's say I have these cells, I had the cells A, B, C, D, F, E, G, H, I. I had these 9 numbers. So what I'll do is, first I'll ask myself, for I being the final position, what was the best position I could have taken as start? Now, obviously, if I take I as final position, it's going to come somewhere over here. That's the first term. So final comes first, that's I. Minus, there is something that has to be taken as start. So obviously, if you want this difference to be max, you would want that this value over here is as small as possible. If this is as small as possible, this whole difference will be as large as possible. Yes, because I is fixed. If let's say I fix as a final position, then the number I put here should be the smallest value possible. And then by another constraints given in the problem, that number, I'll mark this by the grid only. If you are taking this I over here as a final position, you can only take this block to fill up with a number that belongs in this region. Why this region? You cannot take I again. I itself cannot be taken. And I only need to take anything that is on the, because I wanted to go only in the bottom or right, because I'm doing in reverse order. I only want all the numbers from this current cell which are either on the left or on the up, or up and left both part of the grid. So standing at I only want the numbers A, B, C, D, E, F, G, H. The minimum number out of these all numbers should actually take up this block. Let's assume that that number was D. So I know that for sure, if I would have taken I as a final position, it would have been most optimum for me to start at D. And from D, I can follow any pattern, any path jump I just want to do, just to go reach I. And that can be very simple. Maybe I go to G and then to I. Not going to matter, because the term G is getting cancelled. Only difference will matter is I minus D. Similarly, next time when I argue that I am going to make my final position, let's say I found the answer for I being the final position. Next time I'll say I am going to make, let's say, H the final position. So if I make h the final position, my search space is everything to the left of h and everything to the right of h except leaving h. So the space grid which I want to search the minimum number is this one. Out of this A, B, D, E, and G, if this becomes H, whatever number that comes over here should be the lowest possible amongst A, B, D, E, G. And then this ideology can be maintained for every number in the grid. And once that is done and dusted, I will be able to get this whole maximum, this difference for a single number can be maximized with some answer variable. And that answer variable will then store the most optimum two cells I could have taken, which had the largest difference, keeping in mind that I can only go right and bottom according to them, or but in reverse order as I took only left and up. Right. So this is the whole solution to the problem. Now, the next part comes is how do I implement this? Like I cannot obviously brute this out. Let's say I have A, B, C, D, E, F, G, H, and I. Now, if I'm standing at I and I ask you, tell me the best possible minimum in these numbers, can you argue that let me just iterate in this possible search space one at a time, go to every number A, B, C, D, and then maybe take out some variable M out of this, that's the minimum, and then make it I minus M as my answer. That's not possible, because if I do this for every cell, I will have a very large complexity. To be very specific, in an order of complexity, I'll have an N into M square complexity. Why? Because N into M will be required for every cell on an average, N into M again be required to actually get the search space running and get the minimum out of that search space. So this part is required. Now, if I try to analyze these two complexities, I know that this part is very crucial. I have to go to every cell. I want to go to every cell because every cell has to be treated as a final FN, you should say, or final cell I actually reach in whatever grid path I had taken. So this complexity is something that cannot be done. But because this is taking up a large chunk of my complexity, to be very specific, it's taking up, if this is 10 power 3 into 10 power 3 order, that means I have a 10 power 6 order already taken up for my most chunk part of my time complexity. So that means I need the query part, that is this part of n cross m tc again, that is actually just simply finding the best minimum on this search space excluding I, basically, you can say, or the search space excluding that cell itself, or the rectangle or the structure that could have formed from 0,0 cell to, let's say this cell was in x, y cell, whatever, from 0,0 cell to x, y cell, excluding x, y cell. If I can do this in a better time complexity, I'll be good to go. And the argument is, yes, I can do that. How? I can implement it with something called as 2D prefix minimum. What do I mean by this? Now, what I'll do when I say 2D prefix, I will create an extra dimension 2D array of n cross m. And let's say I have the initial structure like, let's say 3, 4, 5, 1, 1, 2, 1, 1, 0, something like this. Then what I'll do is I'll create an extra 2D array that's n cross n. The initial number over here 0 at 0, 0 place is 3. And then all the rest of the places will be filled by a very simple analogy. I'll say that, let's say this 2D space is named A. Then A of I comma j is going to represent the minimum value till I comma j cell from 0, 0 in that, or in that, no, remove that, in that. I mean, in that, what do I mean by say this? What do I mean by this is actually, let's say you want to now fill this position. This position is going to get filled, like if this is 0, 0 cell, from 0 to 0 cell, all the indices I comma j, which are between the boundaries of 0 to I comma j, for both pair I comma j, will be considered, and the minimum out of that will be stored at this I comma j position. So that means this area, this prefix from 0, 0 to 0, 1, because I was trying to fill this position, that's 0, 1, I will find the minimum. How do I find this minimum? This minimum is going to be simply the minimum of, like, I know that out of 3 and 4, the minimum is actually 3, so I fill 3 over here. Next time, what number should I fill over here? the minimum in this block. That's still 3, so I fill 3. Now next time I ask you, what number over here? The minimum in this block should be filled over here. So that means I fill the number 1 because the minimum is 1. Then about this, the block over here. For this block, the minimum is 1. So that is what I fill at being the corner position of this. This is 1. Similarly, this still remains 1. This is 1, this is 1, and this is 0. So this is like a prefix, 2D prefix minimum array I have created. And the relation to actually create it will look something like this. So what I can do is, I can first declare the 0, 0 index as the same number in the grid. Then I can first fill out the upper row and the lower row by simple 1D prefix concept. 1D prefix concept means I'll write the relation that, let's say I'll talk about the row part. So in row, I'll say A of I of 0, that's the first column for all the rows I'm calculating, is equal to the minimum of A of I minus 1 of 0, comma, grid of I of 0. This helps me fill in a 1D prefix manner the minimum in this direction if I traverse to. Similar relation will be created for the first row. So this is for the first column. This is for the column because I have kept I, the changing dynamic variable, and 0 as constant. Next time I'll just reverse these two parameters and I'll do this for the first row, only rotating the columns. And then what I can do is to fill the other positions, it's going to be very simple. Like if you have actually done some sort of question that looks like this, like there are questions in rectangular area filling and stuff like that. 2D prefix and 1D prefix, 2D prefix is something that is very common. So I don't need a very detailed analysis of how this is working, but we get the general idea. So if I want to fill this position, let's say, I obviously will try to fill this position by, I'll draw this polygon over here. If I want to fill this position, initially let's say this position is not filled. This position will obviously will be filled by whatever is the minimum out of this polygon, this, and the number kept over here. So up till here, whatever is the minimum, that is A of I minus 1 of j, then A of I of j minus 1, and then the grid number itself. That's the current number, grid of I of j. Whatever is the minimum out of these three is going to get filled over here. So now if I ask you what should have come over here, obviously like I'll remove these numbers because these numbers were initially not filled, and I showed you how did I fill the prefix, 1D prefix. So 3, 3, 3 got filled, 1 and 1, 1 got filled over here. Now when I want to fill something over here, that would be minimum of 3, 1 and this number 1 itself, that's 1. So I fill 1 over here. Next time I want to fill this position, minimum of the upper part, 3, 1 and this 2, that's the current number, which is actually 1 only. So this gets filled with 1. Now minimum of 1, 1 and the number over here 1 itself, that's still 1. And then minimum of 1, 1 and the number here is 0. So 1, 1, 0, minimum is 0. So I fill 0 over here. So this is how a general 2D prefix sort of a minimum is created. Now once this is done, how does it help me? How do I think that this helps me? This helps me in such a structure that now when I am standing at any cell, let's say I am standing at an x, y cell, then standing at an x, y cell, whatever is the minimum in this part, whatever is the minimum in this part, these two minimums can be taken, and these two minimums, like out of I call whatever was stored as a minimum for this value, whatever was stored as a minimum of this value. And out of these two, whatever is the next minimum, let's say whatever is the minimum out of this value stored in A. So if this is x and y, so A of x minus 1 and y, and A of x and y minus 1. Whatever is the minimum out of these two values is actually the minimum value which would have been there in this whole search space I just marked with black, this search space. And that minimum value can now be calculated in a constant time period because I would have already pre-computed this 2D looking prefix array. to pre-compute this, I know I am only utilizing n into m across time complexity, which is done pre-computation. That's a pre-computation we do. So next time I want to actually calculate for every cell, I can do this in O of 1 complexity. What is the minimum that could have been there in this area? And that's done for every number. So I have a achievable time complexity of n cross m, and this gives me a AC. All right, this doesn't give me a TLE. All right. So what I'll do is we can quickly jump into the code part and understand how we implemented this out. All right, so I've done exactly same thing what I dictated. Take the n, m, create a new vector, n cross m size. Initially, a of 0, 0 is still grid of 0, 0. Then first I have populated over here the first column. Then I have populated over here the first row by the same logic that I showed you, 1D minimum logic, a of I minus 1, 0, and minimum of grid of I of 0, and then the reversed roles. Then I loop from 1 to 1 because already I know 0 row and 0 column are already filled. So 1 to 1, then a of I becomes minimum of these three values, a of I of minus a I minus 1 j, a I j minus 1, and the current number grid I and j itself. So the minimum out of these three is the number that stores in a of I of j. Now I make an answer variable that's initially int min, iterate from the back, so n minus 1 to 0, m minus 1 to 0, take a new number that's b, that's the number I have to find, that's the minimum number, that's initially int max. If I minus 1 is greater than 0, then I will minimize this b with a of I minus 1 and j, that's the just above value stored for the 2D prefix minimum. Then I'll find the right hand side value, that's I and j minus 1, if j minus 1 does exist, and then answer becomes max of answer, comma, the difference. That's the grid of I of j minus b difference, meaning b would have been actually the first cell and grid of I of j would have acted as the final cell for me to make a path and do the jumping. And then when I finally return answer, it gives me the correct expected answer. If I submit this out, you will see this gets accepted, and obviously it's the right solution. Logically, it makes sense. So what about time complexity now? Obviously, time complexity very easily lookable. This is actually like, this is running in O of n solution, this is running in m solution, and then this is running in n cross n solution. Similarly, this is also running in n cross n solution because everything inside that is constant. This part is all constant. So I have an overall time complexity of n cross n, which is actually the superseding complexity. Now what about space? Now I'm using this extra 2D prefix sum space sort of n cross m. So I can name that as my extra space n cross m. All right, so I mean pretty simple problem once you actually get the hang of this observation, and then implementation is like this 2D prefix concept is something that's very popular. So I highly recommend you, if you can check out, you should definitely read about this concept, and it's a very easy concept to understand. It's many times used in grid based problems where sums, differences, everything is asked, so that you pre-compute some data in order to better your time complexity. All right. So I think we can move on to the next problem. That's problem number 4. All right, so find the minimum cost array permutation. Now this is like a kind of a hard problem, I should say, and I'm going to discuss two solutions for this problem. One would be the intended solution, which will obviously make sense and it should work. And then I'll show you a small trick and optimization in some different whole idea. All right, so first let's read the problem. You are given an array nums, which is a permutation 0, 1, 2, so on till n minus 1. And the score of any permutation of 0, 1, 2, so on to n minus 1 is defined as the score being permutation of 0. Let's say you actually make up a permutation. So permutation of 0 minus nums of permutation of 1, this value, absolute value, plus permutation of 1 minus nums of permutation of 2, this value, so on, so on, so on, till the last permutation n minus 1 minus, then the cycle comes back and you have permutation of 0 from the nums. So this is indirectly simply saying that, let's say the permutation I created was, let's say 2, 0, 1. This is the permutation of 2. Yes, for all the numbers from 0 to 2, or the permutation size of 3, but the numbers are from 0 to n minus 1, that is 3 minus 1, that is 2. So it would indirectly mean that, let's say, and my nums array had numbers, let's say A1, A2, and A3. All right, or to be specific, this should be in 0 based indexing. I name this as A0, A1, and A2. So my sum actually would be 2 minus, so I'll take the first permutation, I'll take 2 pairs basically. So I'll take these two numbers, that is 2 and 0. Over here, I'll place this value itself, that's the permutation, that's 2, minus over here, I'll place this permutation index being called in the array. So if I call 0 over here, that's A0. So this is A0. This value. Plus, next time I'll take these two pairs, 0 and 1. So I place 0 over here, minus, but I place 1 over here. But I place 1 in the number, in the nums array I call the first index. So that's A1. Plus, next time I'll take the last two pairs, that is in a reverse manner. So this one and then this 2 in a cyclic manner. So this becomes 1 minus, this is A2. So this is what they have asked. Now, this is the value that is created, that's the score. And obviously, if you change the permutation, like the permutation is maybe 0, 1, 2, then there's going to be a different score. Permutation is going to be 1, 1, 2, 0, there's going to be a different score maybe. So permutation, as the permutation changes, score is going to differ. So they want that you actually get a permutation, you report a permutation which has the minimum score possible. All right. You want the best, lowest score. And for that score, they also want which permutation there is. And then in that, added to that, the hard part that's already there, they've added to that thing that amongst that also they want the lexicographically smallest one. So let's say I have a permutation 0, 1, 2 and I have a permutation 1, 2, 0. Both of them are giving a score X. Then I will select this and not this because 0, 1, 2 is lexicographically smaller than this permutation. Yes. So this is the whole idea. Like it's kind of a straightforward idea to understand what they want us to do, but then it's kind of hard to implement and think of a logic of. All right, so first things first, let us look at the time, like what goes to our first concern is what is the constraints given to us. So n is given in order of 14. So it's very small. It's actually 2 to 14. So because it's 2 to 14, your first intuition might be, what if I create all the permutations and then actually simulate the whole process? So to create all the n size permutations, like for the n sized array, I will require some time complexity, and then maybe for each permutation, I can get my hang of what answer am I actually going to form, what score am I going to form, and then subsequently what permutation should I store. But then this is going to give you a TLE naturally, right? Why? Because you know that n factorial into n is some sort of a complexity that mostly is achieved to actually create the permutation. Or even if you don't demand n factorial is still there. Now 14 factorial being the highest part in n being going to 14 is going to give you an order of 10 power 8. If you actually Google this out, it's actually into something like 8 into 10 power 8 or even 10 power 9 something. So this order is definitely TLE. Because I know I want something less than 10 power 8. All right, even 10 power 7, 10 power 6, something like this, but I don't want to exceed 10 power 8. 10 power 8 is definitely TLE. And if you implement this out, you will get a TLE. All right, so it's not even a argument that if you implement this out and it might pass, it's going to give you a TLE. That means we need a better optimization than this. So this is where the whole idea pops in. Now, by experience, what happens is, when n is actually belonging in constraints from like 1 to 15, 16, something like that, or 1 to 20 even maybe, most of these times, there is something called as bitmask DP, which is used. So if you look at the constraints in a problem and you find constraints to be in such an order, then there is high probability that there's a concept known as bitmask DP that is going to get implemented in this. Why bitmask DP? Because in bitmasking, what happens is in form of a binary formatted number, I'm able to maintain information in form of bits. If some bit is turned on, then I say that information is getting utilized, whatever I represent that information to be. And if it's 0, I say it's not getting utilized, it's not getting used. And in this case, because it's in order of 1 to like it's the maximum order is 14, that means I can maintain a bit mask of 2 power 14 to store the information. And now what information do you think I should store? I will store the information of creating the permutations. How do you think is a permutation created? Naturally, a permutation is created by selecting numbers in a random order from the given array. A given array might be 0, 1, 2, 3, 4, so on till n minus 1. This is the possibilities of choosing the numbers. And I want when number to come only one time, and I want all numbers to come. So I want a random order of choosing. Let's say I could have chosen 2 first, then maybe 4, then maybe 1, then maybe 0. This creates some other permutation. Maybe 2, 4, 1, 0. This is some permutation. Similarly, there can be some other permutation. So what I can do is, in using a bitmask DP concept, I can actually maintain a mask of 2 power 14 size, maximum 2 power 14 size, for which if I say that currently some bit is turned off, this number has not been used, to be added to my current permutation. So I'll maintain some permutation as an array or something, whatever you can call this. And if I say that in my current permutation, this number is not used, so that means the current bit mask value over there is bit 0, meaning that out of the 14 numbers, let's say these were the 14 numbers, let's say the numbers were A1, A2, A3, A4, so on till A14. So if I'll say that my, like from the back side, I'll say from the LSB side, I'll say that, let's say the lowest bit from here, let's say maybe the third bit, let's say, was turned off. That would mean the third number from over here, let's say this was A14, A13, A12. A12 has not been taken because this third bit from over here is turned off, right? If I say, let's say the fifth bit is turned on, it's 1. That means the number from over here, that's the fifth number, let's say that would be, I think, yeah, A14, 13, 12, then this is 11 and A10. A10 has been taken. That is what I'll argue. So this is what I'll represent in the bits. Whichever bit is turned on, I'll say in my current permutation, it has been used, else I'll say it has been not used. So this is the mask I'll maintain. Now what more do I need to maintain? Now remember, in this question, you can obviously start from any number. Like in your permutation, you can obviously start with any number and you can obviously end at any number. So obviously your permutation can have any first beginning and any last beginning. Now why am I saying this? Why am I saying this first and last beginning? Because you have a cyclic order. So if, let's say, this permutation score was looking only like this last term was not there, permutation of n minus 1 minus permutation of perms of 0, then what would happen is you will not be required to maintain something known as a first variable or first term you actually took of your permutation. Why? Because you would have never been required to retrace back to what first number you took. But over here, you do want that. Why? Because if, let's say, you start at some number and you keep that number as perm of 0, that is permutation of 0, then finally when you exhaust to create the final permutation and you maybe reach the full capacity of the permutation being the size of n, then you will require this perm 0 number back, that's the first number back, to actually get the last value, that's perm of n minus 1 minus nums of perm of 0. So besides to a index, which is actually the current index that's actually going on and on to choose what current number should I take up in my used state, I also want to maintain a first index. All right, now there might be some confusion regarding this part, that maybe you can argue that on a better optimization level, this is also not needed, but I'm not going to discuss that. All right, being the part that this is more intuitive, right? This clearly is more intuitive to maintain first index, because maintaining first index will help me directly fetch the last number used for me to calculate this last core value getting added in the final score. So that means I will be obviously required to maintain an I variable, that is the iteration that is actually happening, jumping of i's in the all possibilities of unused numbers. And then I will also require first state over here, that's the number. So this means that what I can do, like I'll create the DP like this, although you can again optimize it as much as you can, but then this becomes highly intuitive. So I'll maintain the DP to have 3 states. One is going to be this first, next is going to be this I state, that's the current index that I'm saying, and then that I will have the next state as the bit mask, that is the current bit mask to represent how many numbers have been used, what numbers have not been used, what information do I have, what is 1, what is 0. So this is bit mask. So now if I ask you what do you think is the time complexity, you will obviously argue that I will have a first, like this first index can vary anywhere from 0 to n. So this is n. Into I index will obviously have an n complexity. This is n. Into bit mask is always going to have 2 power n to maintain. So the states are n into 2 power n. Moreover, in this, obviously you can imagine that in permutation logic, I will, like at a specific order, like let's say I have the current numbers I have used up is, let's say, 1 and 2. And the possibility to use numbers are left are 0, 3 and 4. Let's assume. So you will have to iterate in the possibilities and take up all possible calls of recursion to actually get hold of these 3 possibilities. So maybe a 0 can come over here, maybe a 3 can come over here, maybe a 4 can come over here. So for that, you will require a for loop inside the recursive logic itself, which will add on an n complexity. So overall complexity that comes in an order is n cube into 2 power n. And now if I tell you for a n being max in 14, if you actually calculate this by like a calculator, 14 cube into 2 power 14 is actually some number. It's a number that's in order of 4 into 10 power 7. Now this is just high borderline to 10 power 8, but this is going to get accepted because it's obviously less than 10 power 8. So you will have a high time complexity. That's definite. There is a time complexity. This is a significant time complexity, but then because this is lower than what is the even upper bound to actually exceed the limit and surely get a TLE, this is going to definitely pass. And that's the whole idea behind the problem. All right. So what I'll do is I'll show you the code part and let's try to follow up with the code. How is the stuff getting handled? And then we'll see what do we need to do. All right. So I think before the code, I need to discuss one more thing. Over here, the added part to this is you also want that you return that permutation. You're no longer required to only find the score, but you also want to find the minimum, the permutation that gives you that score. So I'll give you a general idea. Like what I'll do is I'll dictate this. We will be reconstructing our array back. How do I do that? Imagine that I have found out my score. Let's say my score was X. If I have found out my score to be X, that's the smallest score, what I'll make sure is along with X, I will also save the best starting position. So let's say the smallest score achievable was X and it was achievable when the first number that was part of the permutation that could have just begun the permutation, the first number in the permutation was, let's say, 1. Let's say that the best possible score that was X, and the best number that could have started to give this X score was a permutation that starts with 1. Now what I can do is, by that same recursive solve function, I can in a recursive structure reconstruct the array after this. So once I place 1 over here, what do I need to place over here? I will obviously place a number over here which gives me the next state to achieve a score. So when I keep it over here, the current score is initially 0. Next time, I will say that whatever DP as a state stored to make a new score, let's say to come over here, the score was Y. To create a new score Y, the best possible next number will be reconstructed out of the possibilities. Let's say the possibilities was 2, 3 and 0. So let's assume that, let's say, if I would have kept 3 over here, I would have actually gotten the score to be Y. That is, in this case, like Y as in 1 minus nums of 3, right? Like this way, which was actually stored in the DP because DP had stored all the possible states. So you can actually relate this sort of a problem, like it's a reconstruction problem with, I'll give you hints over here. You must have done problems, like you can explore these problems. There is something called as a Dijkstra problem, that's the shortest path problem. And in that, many of the times, like what the question asks you also, it asks you what is the shortest distance between the source node and destination node. And then it also asks you that tell me the path from source to destination. So in that also we kind of do this reconstruction sort of an analogy. We store the parents and then we try to retrace our path back from the destination to the source. That would have given me the shortest path. One more example I can give you is creation of the longest common subsequence. So that is LCS, longest common subsequence. In this also we create a 2D DP sort of structure, and then if the question moreover asks you tell me the string which is the longest common subsequence out of the two strings, let's say X, Y, in that also we try to retrace our path from the bottom cell to the top right cell. So these are like two popular problems where retracing of the whole logic is done. So this is kind of the same logic which we'll apply over here to reconstruct our permutation array back on the basis of the values I have stored in the DP, which were initially calculated to calculate the minimum best possible score. So once I've done the score calculation, my DP is done and dusted. My DP is done and ready with the best possible states. So using my DP, I can now further put my answer in the reconstructed format form. Knowing that this could have been the first number, I can again construct one at a time the single numbers which I wanted to place. So I place, let's say 1, 3, then maybe next number, best number could have been 2, then maybe 0, and then I could have said 1, 3, 2, 0 was the actual permutation which would have given me the best possible score that is X. Alright, so you must do this question on pen and paper yourself, and this is going to take some amount of time for you to understand the whole working. But then this is a very classic problem and application of bit mask with the DP, along with the reconstructing sort of a approach I told you. And I've given you similar problems also. So post this contest discussion, you can actually explore these problems yourself so that you get a hang of how problems can be constructed. And sometimes problems also ask you, along with the best achievable value, to also give you, they also ask you the operations or the path or the structure which would have given you the best possible value. And this is the example of that question. All right. All right. So what I'll do is I'll show you the code part then, and we'll understand what I'm going to do. All right. So let's start over here. You have the n size taken extracted. I create the DP. Now DP obviously has the states n into, now the other state is 1 left shifted to n times. That means 2 power n. So I have created the DP to have states n cross n into 2 power n. And initially everything is -1. Now I have the answer variable, that's int max. And then the first parameter, the first variable, that's initially 0. Now this is going to store the first value that I should have placed. So I obviously iterate from the number 0 to less than n, because the numbers, permutation numbers can be 0, 1, 2, so on till n minus 1. Then if I call this function f, if this function f, I'll discuss what this function f is doing. If it pops up to me a score value that's lower than my current answer, that's the current score value, then I declare my first variable to be I, meaning that this is where I would have started my permutation from, and my answer gets updated with this value itself. All right. So now let me just stop over here and actually discuss this function quickly. All right. So look at what I'm passing over here. I'm passing I, 1 left shifted I, dp nums and n. So dp nums and n are constant, obviously. This is the first variable. That's the first number that I'm going to use. I'm passing this because when I reach the end, I want to add onto this value. Then I have the previous variable, or you can say the current previous variable. That's the previous value which I had. And then the mask. So first what I'll do is I'll count the number of bits set in the mask by using a built-in popcorn function. This is the part of the STL library. If the count of the current bits in the mask value is equal to n, that means I have exhausted all the unused numbers and my permutation size has reached n. So if that is the case, I will return dp of first or previous of mask equals to absolute value between nums of first. This gets called so this is the place where I will be now using the first parameter for me to use, because I wanted in a cyclic manner again the first value minus previous. Previous would dictate the just previous index which I took. So this happens, this is the base condition which happens if I feel that I have exhausted all the numbers, or meaning the mask built-in pop count or the set bits in the mask value is all 1. And then this is obviously the saving state in a DP. So if it's already not -1, I return that because I know I've already pre-calculated it. Then I declare that value to be int max initially because I want to minimize the score. Go to all possibilities from 0 to less than n. I check that is this number currently not set in the mask. So how do I check it's not set in the mask? 1 left shifted I ANDed with mask should give me a value. If it gives me a value 0, then not of 0 will be 1, meaning it is not set. And if it is not set, it is a possible number that can now be added to the permutation. So if it's a possible number that can be added to the permutation, I update dp of first of previous of mask to be minimum of dp of first of mask, previous of mask, comma, this value itself, comma, what score do I add? Absolute of previous minus nums of I. So previous is the previous I did I take, and then I becomes the current value. So previous is the previous index I would have maintained, and nums of I, that's in the I part, I being the permutation, like let's say PRM of 1 if PRM of 0 is over here previous, and that gets called for the nums part, so the number gets extracted. Absolute difference of that plus call the function again. In that function, first gets passed as it is. The previous now becomes I because the current I is the new previous. And then I have the mask which gets added with the value 1 left shifted I, so that I am able to turn on the value of that ith bit in the mask, because now I know I have used this ith number, or this ith number from the permutation values possible. So I need to turn it on the mask, and then dp nums and n get passed as it is. And then when I finally come out of this, I can return dp of first or previous of mask for the other function calls to store that value. Now what this does is, now you can see I am going to do this operation for all the possibilities of finding the lowest possible score. And every time I find the lowest possible score, lower than before, I am updating the first. So when I finally end this for loop, what I'll have in the answer, I'll have in the answer the best possible score, minimum score, and in the first variable, I'll have the first number that would have been used to create such a permutation to give me a best possible score that I showed over here. Let's say x, and that first number could have been, let's say, 1. Now I want to recreate the permutation. So this is the permutation I want to return, PRM. I start off this keeping as this a vector, and then I've written a lambda function over here. That's the backtracking, retracing sort of a function. I call this by passing the, this lambda function is kept over here, and I'll call it over here indirectly. What will I pass as the first variable? First variable will be passed directly as first only because that's the first value I want to pass. Previous is also first because I'm starting with previous only, so that's not a problem. Like in graph problem, you must have seen I take a parent as -1, so it doesn't matter. The first part I'm starting off, so previous is also first. That it gets handled automatically. And the mask has to be initially set with 1 left shifted to first. Why does it have to left shifted like this? Because it means that I have utilized the first value, so the mask value needs to be initially 1 left shifted first. So that would set the first hand value bit in the whole mask of 2 power 14 maximum order, and that is the initial mask that gets passed. Now I again built in popcorn of the mask value. I push back in the perm the previous value because I know this is the next possible value that could have been used to create the permutation. If index becomes equal to n, then I return because I know I have found my permutation. If that is not the case, same logic copy pasted from the DP side. So if you can see directly, again iterate from 0 to n, check whether that value has not been used. If it has not been used, then this is the crude logic. Then if it has not been used, knowing that in the DP I have stored the best states, what I'll check in the DP of first being first, like over here also first is written, over here first is. So first is still there because I know first is constant. But see this, the current value that is I, being that I use the I value, mask plus 1 left shifted to I, that is if I take this I value, I would say that this value has turned on. If these three states, first I mask plus I of I left shifted to I, plus this is obviously storing the score, plus absolute of previous minus nums of I. So this is the score that would have come from taking previous minus nums of I. If this is equal to dp of first of previous of mask, that is not took it, that means this is actually the state I would have gone to. And if this is the state I would have gone to actually, while actually doing this recursive function, I can actually call this backtrack function again with this first, previous becomes I, mask plus 1 left shifted to I as it is. All right, so you can directly clearly see over here. And then I return. So when I've actually end this backtracking structure, the permutation array is going to store the final best permutation, lexicographically smallest permutation, and the best permutation, which gives me the best possible score. All right. So I know that this is going to be a tough problem to pick up at first. And this definitely requires prerequisites of bit masking plus DP. So only and only if you you can attempt some bit masking and DP problems or the basic structure of bit masking and DP, and then come back to this problem to understand it again. But once you get the hang of it, the states are going to be very easy to understand. All right. And then this retracing part also is going to be very easy to understand once you get problems like the shortest path, LCS and stuff like that, where retracing and reconstructing is done. If you know the hang of it, you will directly observe that, yeah, this can be done to actually create back the permutation, which gave me the best score. All right. Now, what is the time complexity as we discussed? Time complexity is going to be obviously n into n into n into n. N into n into 2n, that is the states of the DP, into n again. For this, you can see easily, I'm doing this loop, right, inside every recursive call. So that's in n order also. So n into 2n, that's the DP states, and into n again, that's for per each. And that's the superseding term. So this gives me approximately, you can write this as n cube into 2 power n complexity. And then what about space? Now, obviously, same space, I'm using DP, and DP space is actually n square into 2 power n size. All right. So if you see I'll submit this out, this is going to definitely work. It's going to get accepted, and it's obviously going to get accepted because this is the right solution. All right, so I think you have we are good to go on this part of the structure also. Now what I'll do is I'll quickly, like in 5 minutes, show you one more approach to this problem. And why do I want to do that is to actually show you that this problem could have been also approached with one more concept known as basic concept. Everyone must be familiar with this concept. This concept is called bit masking. This concept is called backtracking. All right. So where is the code piece I have? Yeah, this is the code piece, I think. All right. Yeah. So what do I mean by, like, when I say that? I mean there's one more code piece. I think this one was this, if I'm not wrong. Yeah, yes, this is the correct code piece. All right, so I attempted this problem in a different structure also. So naturally we discussed the first part of the problem. Like we obviously discussed something that was, if I brute out the whole solutions, if I calculate actually something in a simple saying that what if I calculated all the permutations, I'll have an n factorial complexity. And due to this n factorial complexity, 14 factorial is not going to work. Obviously it is not going to work. Yes, 14 factorial directly is not going to work. But then there is something called as backtracking. Now, backtracking undergoes an inner logic that is actually called pruning of the recursive calls. What does it mean is, by some very smart if and else check, what you can do is, in a normal recursive call to calculate permutation, you can prune out some permutations which you don't want to work, or which you obviously wanted to not go beyond. Let's say you were in your tree somewhere like this. And let's say after this structure, all the nodes below this, leaf nodes below this, were the nodes which were futile. Somehow, if you were able to gather the information that all the recursive calls below this node would have been futile, you can just prune out this part and not just call them. And if you do that, if you're able to do that somehow, your complexity, although will have an upper bound of 14 factorial, it is still going to pass. Now, a classic example of this is actually Sudoku solver. All right. Sudoku solver is a classic example of such problem. If Sudoku solver you search up in Google, you will see that a time complexity of 9, like Sudoku is a 9x9 matrix. Like I'm assuming as you take a standard 9x9 matrix. So you will have approximately, in that size, you will have, for the 9 numbers and a 9x9 matrix, a standard solution is actually in 9 power n cross n. Where n is this, like n is taken as the size of the matrix in that case. So being 9 combinations, you have 9 power n cross n solution. Now this is not going to work if n is high, not very high, just like high enough, maybe in 10 to 15 order, it's not going to work because 9 power 15 is going to be very huge. But then if we implement Sudoku solver, or actually we do implement Sudoku solver with something called as backtracking, you can read about it online, we are able to bring this upper bound down and then it works. So you can solve this problem on Leetcode also as practice. You can solve this problem on GFG also. You'll get this problem directly. And if you look at this problem, you will understand that although my upper bound complexity is still 9 power n cross n, but it is still works because pruning is done, and pruning on an average is definitely reducing my complexity. So this is something I have done in this solution also. Now, I did wanted to discuss this as a prime solution because there is no specific proving to what time complexity is this solution running in. You know the upper bound is still going to run in n factorial. So this is a simple permutation calculation. But what is the actual complexity? How, where and where would the permutation would have been pruned actually? You cannot prove because pruning is done and it's done on a dynamic input. As the input changes, pruning will be done maybe pruning could have done over here, meaning pruning could have been done over here. Maybe you could have cut out this structure, cut out this structure. You never know. So because of the dynamic input, you cannot just tell for test cases, a file of test cases, that what would be the average time complexity of this. But we you can maybe read about this online also, that generally pruning always works. It's always present if you actually are able to implement this. It's called actually backtracking. The whole phenomenon is actually called backtracking. And by that you are able to reduce although the upper bound is very high, still the average complexity turns out to be very, very low, and it runs much, much, much quicker than the expected time complexity. Alright, so if I discuss this question now quickly, this is not going to be the prime solution obviously, but then you need to know the concepts. Backtracking is also something that's present and gives you added homework that you can actually try out Sudoku solver and stuff like this, backtracking problems also, to get the hang of how beautiful the concept of backtracking is actually. Alright, so in this I'm going to do the basic stuff. I'll say that I had the nums array, I had something called as a used vector, what number I've used, what I've not, the permutation array that I'm trying to create, and the index. And then I have also something known as the sum, that's the current sum. So why I'm maintaining this sum is, you will look in some time. So I have a minimum value that starts with 1e9. I have the answer vector that I want to return. I'll call the use vector to be initially everything false. The permutation is empty. Call the backtrack function nums use perm 00. Then what I do is, this is actually the line. For fun time, just ignore this line. I'll simply say, forget this line was there. I would have simply said perm.size is equal to nums.size. If that happens, that means the current permutation has become equal to nums permutation. If that is the case, then what you can do is you can simply add on the first sum to that perm back minus nums of perms of 0. This is the cyclic last term which we wanted. And then if you can simply check, is the sum less than min val? If it is, then min val becomes sum and answer becomes permutation. So you finally get, by this you would have received the best logical lexicographically smallest permutation with having the lowest minimum value. That's all right. And in this case, you just simply iterate from 0 to use size, and then whatever is not used, you mark it, push back, then come back, backtrack, and then pop it out. So this logic is going to be pretty simple. Like, it's not going to be pretty hard to understand. I'll also attach this code in the video itself, at the end of the video itself. But this line is of importance. Now, what I've done over here is I have kept a very direct check at the very top of the backtrack function that if the current sum exceeds the minimum value, then I return. Now, what is this going to help me do? Let's say I was creating permutations. Let's say I fitted up 1 inside it, 2 inside it. Let's say I had the number 0, 1, 2, 3. I had fitted 1, I have fitted 2. And then let's say the current sum which was there was x. Now, if I know that after fitting, let's say 0, the current sum becomes greater than x, let's say the y sum becomes greater than x, then do you think I should go beyond this tree anymore? I know that anything beyond this is exceeding the sum. So if I've already gotten a minimum sum that looks like this, do I want to go any further? No. So what I'll do is I'll prune this out. I'll prune this part and I'll not go any further. This is what will help me, this line. This line is going to help me do that. If the current sum that is there exceeds the minimum value, then I know that I don't want this permutation at all. So this minimum value has already stored a good enough value of the a good enough permutation that got created. Like, let's say some permutation got created of, let's say the first permutation was 0, 1, 2, 3. This permutation got created. It had a minimum value. Now, compared to this minimum value, if I ever create some sum that exceeds this, so halfway through, I can just come back. I don't need to go any further. And this is the logic behind backtracking. This is called backtracking. So even in Sudoku solver, we halfway through can come back if you don't find possibilities. And this is what we are doing in this. Halfway through, we will prune back and come back on the argument that above this, the sum is going greater than the min value. I don't want that. So it's no need for me to even search those nodes. All right. So this is the whole logic, and this is also getting accepted. It's getting accepted in, I think, 2000 milliseconds. It's clearly visible. All right. So you can also try to understand this solution. This is also one of the solutions, might be much easier for beginners on also, but then the expected solution is definitely this. All right. So quite a lengthy and tough problem, but then again, new things to learn every day. All right. So that brings us to the end of our PCD post-content discussion. I hope you liked it. Thank you.